Welcome to this session on the vSphere distributed switch, the best practices for NSX. My name is François Tallet. I am a product manager in the NSX business unit, and I'll be presenting with Rajiv Krishnamurthy, who is a director in ESX engineering, and more specifically is responsible for everything that is VDS related. So he's the right guy if you have any kind of very technical question. While you read the disclaimer, I would like to mention that 1 hour is very short for us. We removed some content so that the session fits in 1 hour. So I'll try to skip the session until the end, the question until the end of the session if possible. Rajiv and I will be there. We can go outside and stay for as long as you want, but we'll try to hurry up during the flow of the presentation. So I'm going to start with a few words on the agenda. Well, three main sections. We'll have a first section that will introduces some few concepts about the VDS, something that will be necessary for the next part. Then one of the main section will present the uplink connectivity, how to properly configure and connect your switch to the physical infrastructure, and the last part includes some troubleshooting and operation topics, let's say. So without further ado, let's start immediately with introduction and architecture. Before I start, by the way, I didn't say much about myself. I'll tell you a bit more about that. That's not really relevant at that stage, but who in this audience is more of a network admin, or at least has the responsibility of network admin? So I would say 25 to 30%. Who is more of a server admin? Okay, this is VMware, so we have a majority of server admin here, I guess. And storage? Okay. So I would say 20, 25, 50, 25, something like that. Good. So the first slide, what is NSX? I'm not going to spend much more, a lot of time on that. I'm pretty sure you've already heard about that in other sessions at least. But basically, this is VMware's network virtualization solution. Our goal is to provide you with a virtual version of pretty much every switching networking functionality that is possible. So from the most basic one, like switching and routing, up to the more elaborated one, like load balancer, firewall, VPN, L2, L3, VPN, etc. How is this going to be implemented? Well, we have several layers, if you want, in our product. The lowest level, closer to the data plane, is where this software is going to be implemented on your hosts. This is a data plane, basically the code on your host that is forwarding the traffic to its proper destination and that is implementing the different functionalities I mentioned earlier on. We have a control plane, obviously. This is a kind of cluster of virtual machines for scale out and redundancy. And we have complete isolation control plane data plane, meaning that should the control plane fails entirely, like the cluster is disconnected somehow, even if it's highly redundant, well, we're still capable of forwarding traffic in the data plane on the code, using the code on this switch, on the hosts. Then all this is controlled by the NSX manager. The NSX manager is a single point for configuration of the whole data center. That's where your management application will do its REST APIs, for example. So you don't have to go and configure individually devices in this network. Everything can be controlled centrally. And above, this is not really NSX, we have this cloud management system, the vCake, OpenStack, etc., that can take advantage of our product. So, of course, this session is going to be concentrating closer to the data plane where the VDS lives. This is mainly a data plane functionality, even if you see that there is a little more than that. So the VDS, the vSphere distributed switch, I would like to mention, of course, that it is not a new functionality of NSX. It's been there for a while. And by the way, we put a little sticker on the top right of the slide when we're talking about something that is not really related to NSX. So the VDS, again, has been here for a while and is an enhancement over the vSphere standard switch, the VSS, in the way that the VSS is managed on a per host basis, whereas a VDS provides you with a simple representation of a logical switch that is spanning the whole network. So you can attach your virtual machines to this virtual switch that is spanning the whole network. You don't have to know where this virtual machine is. If you make a configuration to the port where this virtual machine is connected, automatically the VDS will go and configure the right hosts in your network. So again, the added value is this global configuration. And by the way, who in this room is still using the VSS at their main virtual switch? Few people left. Who is using the VDS nowadays? The vast majority. And who is using a third-party switch, virtual switch? A little bit also. Okay, so that's a very good evolution. That's where we want you to go, frankly. And well, it has evolved. I've been told that last year we were at 75% for the VDS here. I would say we're probably at 90, even more. So a few concepts I would like to introduce about the VDS. You probably know about them, but just to mention them, the first-class citizen here are the DV port, the port where your virtual machine attaches. So the virtual machine has a VNIC that is connected to a DV port. And similarly, we have a DV uplink, which is basically the representation of the physical connectivity of the VDS to the network fabric. Another simple concept that we're going to use over and over is a DV port group. A DV port group groups several ports together, several ports that have the same connectivity characteristics, in particular layer 2 connectivity. And we have the matching DV uplink port group for the uplinks. So far, nothing special. So that was a global view of the VDS. Now let's go on a per host basis, if you want, a more local view of the VDS. So of course, when you are running a virtual machine in your data center, well, it looks like it is in the data center at the high level, from the high level perspective, but eventually this virtual machine is running on a particular host, right? So here, for example, VM1 is on host A. And that's where we'll have the code implementing not only VM1, but also the DV port where VM1 is connected. There is more than virtual machine that need to send traffic to the network. We also have some services, so some kernel services. Here I've represented the management, HJ and vMotion, but we have several others that you probably know. So those are kernel services. They have what we call a vMechanic, and they also connect to a DV port in order to exchange their information with their peers. Okay. So in its first incarnation, the one that you're using without NSX, the VDS is backed by VLAN. What we mean here is that there is a one-to-one association, if you want, between a DV port group and a VLAN in the fabric. So the DV port group is the virtual side of the story, and the VLAN is what, well, the way it is implemented, if you want, on the networking infrastructure. So I'm a network guy. Frankly, I hardly understand the difference between VLAN and DV port group. For me, it's roughly the same. So the problem with this VLAN-backed VDS is twofold. Well, first, it introduces a dependency between logical and physical. So, for example, I have here a DV port group that is created, this blue DV port group, which is backed by VLAN 1. If I want to create a new DV port group in my infrastructure, so this is a logical operation, right? I go to vCenter, I create a DV port group. Well, the problem is that I need to have now a second VLAN to back this new DV port group. So we have a dependency to the physical, meaning that when I create this stuff on the logical side, typically this is a server admin thing, I need to make sure that there is some work done at the level of the network, and that's a job for the network admin. This is going to slow down considerably your operation. That's one of the main issues, I would say. Another problem is that it requires what I call end-to-end layer 2, meaning that you need to span this VLAN on your whole data center. remember, you don't really know where your virtual machines are going to be positioned, so potentially you have to provision this VLAN everywhere in your network. And again, so I'm a network guy. I've been working at Cisco for more than 15 years on layer 2 before joining VMware. And I know by experience that most customers would like to avoid running L2 end-to-end. I'm not going to trash layer 2, but let's say that one of the problems with layer 2 is that if you have a local problem, it can, basically when it fails, it can result in a global loss of services, if you want. So local problem, local issue, global problem, if you want. So many customers are trying to get away from layer 2. And by the way, just one last thing about this layer 2 aspect, about the pre-provisioning of VLANs. That's why also, as network engineers, we see our server guys coming and say, well, I need 4K VLANs everywhere. It's not because this customer needs 4K VLANs. I've not met any, actually. You probably need 10 VLANs. It's just that you don't know which one, and you might want to add some later in the future, and you don't want to have to depend on the networking team. So that's why you're going to ask for 4K VLAN in one shot, so that's it, you're covered. Unfortunately, this doesn't work well in terms of scale on the physical infrastructure. So how is NSX going to solve that? Well, basically using what we call an IP overlay, which is, in our case, going to be VXLAN. I'm not going to insist too much on VXLAN, on the specifics of VXLAN, because for us, VXLAN is just one encapsulation, one tunneling mechanism like any other. The reason why it was picked, it's an industry standard supported by different other vendors, not just by VMworld. And actually, I just received an email yesterday. It became an RFC. So it's not only an industry standard, it's also an IETF standard as of yesterday. So what VXLAN is going to do is that it gives us the capability of sending a frame through an IP fabric. So this frame is encapsulated by the end of our tunnel. This is what is called a VTEP, VXLAN tunnel endpoint. So your L2 packet is presented to VTEP. The VTEP encapsulates this frame, and the frame is transported as an IP packet across your network to a remote VTEP where it's decapsulated and forwarded to its final destination. So this is how we're going to avoid layer 2. Something else I would like to mention here, why an IP encapsulation? Well, obviously because IP is a prevalent networking technology. It runs over any medium, over any technology, networking technology. If it's a networking technology, it can run IP basically. And it also allows you to use very generic switches or routers. IP routing is the most basic function you can expect from a networking gear. It is not vendor dependent. It is not even requiring the cutting edge latest technology. So you can mix generations of routers in order to provide this functionality. Also, a last thing I would like to mention in this VXLAN header, I'm not going to go into the detail of the packets. It's just that we have what we call a VNI, a VXLAN network identifier. This is roughly equivalent to VLAN ID. We have 16 million of them. That's basically, just consider it's a VLAN ID. So how is the VDS going to use VXLAN? That's a service like any other. You remember I made earlier on a slide with some few services, HA, I don't remember, vMotion, stuff like that. Well, we have a local service now implemented on a host. And this local service is a VTEP, a tunnel endpoint. It is capable of taking a frame, encapsulating it in IP, and sending it over. And in order to do that, it requires network connectivity, so it's connected to its own DV port in its own DV port group and so on, which is backed by a VLAN, etc. By the way, you'll notice that the VM now is connected to a logical switch. That's how we call a DV port group now when it's backed by VXLAN. So if you were confused about this terminology, just like I was, VXLAN-backed DV port group is pretty much like a logical switch. It's like a VLAN. It's a broadcast domain. You might even see in some UUID virtual wire. All those terms are the same. That's a broadcast domain. It's simple. So L2 connectivity, meaning that now if my VM1 wants to send traffic, it sends it to its DV port, And the DV port itself will use a VXLAN service local on this host to process the packet further. So we're having here a representation of this. We have VM1 that is going to send some traffic to VM2. They're on the same logical switch, meaning that they have L2 connectivity. We're not going to talk about routing here. But they're on different hosts. So we need somehow to make sure that this packet can be communicated over the physical infrastructure. So first, my VM1 sends a packet to its DV port, which in turn forwards it to the local VTEP. The local VTEP adds the VXLAN encapsulation, which is IP, UDP, VXLAN header. Then it is forwarded across the physical fabric as an IP packet, right? Not as native L2 traffic in a VLAN, as an IP packet. The VTEP I'm going to mention it straight away, the VTEP has an IP address. So this packet is looking like if it's coming from the IP address of the VTEP, and it's going to the IP address of the remote VTEP. The VTEP on host B is decapsulating this frame, and voila, you're getting it forwarded to VM2 on the other host, on the other host. So the beauty of this, of course, is that now, in my logical infrastructure, if I create a new logical switch, well, I create my brown logical switch, what used to be logical switch, DV port group B, it's logical switch B here. Well, everything works the same. I don't have to do anything on my physical infrastructure because the packet that this VM4 is going to send to VM3 is still going through the VTEP. And from the perspective of the IP of the networking infrastructure, it's still an IP packet exchange between those two VTEPs. No change in the network. So the key word here that we're going to repeat in this presentation is that we've completely decoupled the logical from the physical. Now you, as a server admin, you can create a new logical switch, and you don't have to synchronize anything with the networking team because from their perspective, it's all IP traffic. The physical infrastructure is not aware of the ID of those logical switches. You know, you have a VNI. Basically, I told you it was like a VLAN ID. They don't care about that. They just see an IP packet. So we have a short demo, which is illustrating that. And the only thing you have to see here is that we can create this logical switch and have a ping exchange between two virtual machines without any configuration on the network. You will not see this screen switch to the console of a router and make some configuration changes. So first, just an overview of our network. We have basically two clusters with some hosts. We have a control cluster with our NSX infrastructure. And we're going to add two virtual machines on two hosts that are located in the first cluster. What we're going to do is that we're going to create this logical switch I was telling you about. So we create a brand new logical switch. It is backed by a transport zone. I'm not going to go into the detail of what it is. This is if you want a representation of the instantiation of the physical network. So our logical switch is up. Right now there is nothing connected to it. We're going to connect two VMs to it. We assign ports. And then we're going to start the VMs, and we're going to launch a ping from one to the other. One of the VM is already started. We're going to start the first one. The other one is already started, you'll see. And I'm not going into the detail of the IP address, etc. But again, the goal is to show you that I can go into my vCenter, do a creation of a new logical switch, new virtual machine, etc. Everything can be done without interaction with the physical world. That's the benefit of the model. So we're showing you the interface. And here comes our ping. And of course it works. It's recorded demo. That's the beauty of it. Note that it's easier to record this demo in Camtasia using a real environment than faking it. So rest assured, it's real. OK. So let's move on to our second part, which is more about how we configure this VDS. And that's where we'll have some few best practices. The first one, which is relatively obvious, not just for NSX, but for networking in general, is that you don't want to depend on a single physical failure. So we're going to recommend that you connect your host to 2 top-of-rack switches. And by the way, just a side note, those are recommendations. It's not a rule by any means. So don't think, oh, I have to connect my host to 2 different top-of-rack switches. Actually, you have some customers that have a rack as a single failure domain. If there is anything wrong with this rack, they bring it down. They have a standby rack ready to take over. So it really depends on how you set up your network. But for those kind of customers, they don't care about redundancy to the top of rack, obviously. So still, for the majority of you, I would guess that you're interested in connecting your host redundantly to the network. And today, well, we can connect using up to 32 uplinks. And today, the most prevalent technology in terms of uplink connectivity is 10 gig. So you're probably going to end up with 2 times 10 gig. And this is what we recommend you move to if you still have n time 1 gig. And by the way, quick poll here. Who is still using 1 gig connectivity on their hosts? So a little bit, I would say. Who has a mix on a particular host, has a mix of 10 gig and 1 gig? OK. And who is using 10 gig connectivity? Oh, wow. OK. So indeed, it matches what we expected. I mean, 10 gig is now the main connectivity option for your servers. So of course, now when you're using a limited number of uplinks, there's no way you're going to dedicate an uplink to a particular infrastructure traffic. You don't want to dedicate a 10 gig uplink to your management traffic, for example. So we recommend that you map all your VM kernel interface or your VM KNX to the VDS. Forget about the VSS now. You migrate, and I know from the previous poll that you already did that anyway, but connect all your interfaces to the VDS and share those 2 uplinks with all your infrastructure traffic. We have NIOC, Network I/O Control. This is, well, we're not going to elaborate too much on that because it's not NSX specific for the sake of time. But in a nutshell, what NIOC allows you to do is that you can, for a particular class of service, you can specify a bandwidth limit, make sure that it doesn't go beyond a certain amount of bandwidth. You can provide a share of the bandwidth. You can set a share of the bandwidth for this particular traffic. And you can also set the QoS parameters that will be used on the physical infrastructure. So use NIOC to manage your different category, your different class of services on your uplink. But don't use physical separation if you want. So also, we now have some few NICs that are capable of doing part, if not all, of the VXLAN encapsulation in hardware. And of course, this will improve your performances, so we recommend you use them. That's, again, one of the reasons why we're using VXLAN. We, as VMware, don't really care about the encapsulation in theory, but because this is an industry standard, you'll get this kind of support, which is always welcome. And at last, some few recommendations on how to configure your physical switch. We recommend that you configure your port as edge from the spanning tree perspective. So in Cisco's terminology, it's port fast. It means that you're skipping the initial blocking stages of the spanning tree and go forwarding immediately. You typically only do that on ports that cannot lead to a loop, right? Because you're basically short-circuiting the discovery phase of the spanning tree. And this cannot happen because with our VDS, because the VDS will never, ever switch back traffic it has received on one uplink in one of its other uplinks. So it will never be part of a loop with the physical infrastructure, as it is today at least. BPU guard recommendation does not really make sense anymore now that the VM traffic is encapsulated with VXLAN, because even if your VM was sending a BPDU, your physical infrastructure wouldn't see it because it would be encapsulated in an IP packet. But just in case, I mean, a host is not supposed to run spanning tree, so that doesn't cost you much to configure BPDU guard. What it's going to do is that if it receives a BPDU, it will shut down the port. So that I would say it's more of a security policy than a requirement. So that's a kind of holy grail for many of the network engineers, is that with NSX, you can really get rid of this end-to-end layer 2 fabric. So again, as I've worked a lot on enhancing this layer 2 fabric in a previous life, but the benefit is that you don't have to get the advanced features that have been developed by network vendors and that generally require new hardware. You don't need L2 connectivity because we're going to rely on IP only. Note that I'm not saying that NSX would not work on an L2 fabric. It would. The trick is that you don't have to. And again, you can rely on hardware that is generic and with the technologies that has been proven being stable and scalable for years. So the way it works is that your VTEP, right, has an IP address. I told you, the IP address of those VTEPs can be in different subnets, meaning that you can basically have a small layer 2 domain that is terminated at the top of rack and basically don't have to bridge anything on your network. Again, local failure. Local problem means global failure at layer 2. So if your layer 2 domain is very small, well, local failure means local failure too. That's why you want to reduce the span of your layer 2 network. And by the way, this recommendation applies to not only the VXLAN VTEP traffic, but to all your other VM kernel interfaces. So earlier on, it didn't make any difference because you needed L2 connectivity for your VM traffic. So as soon as you're enabling, as you're extending few VLANs across your network, well, you can pretty much extend all of them. But now that you can segment our traffic at L3 at the top of rack, well, it makes sense to do the same for everything and get rid of layer 2. Now I would like to go over some few load balancing options. So a first word of warning is that 2 times 10 gigs is never equivalent exactly to 20 gig. All those load balancing mechanisms are just spreading the traffic across the available links. So assume we have 2 links. We have a group of packets. We're going to make a distribution of those packets across those 2 links. It's kind of statistical distribution. If everything works well, you have an even distribution and you're maximizing your bandwidth. But note that it really depends on your distribution packet as much as it depends on the technology you use to spread those packets. So for example, suppose you want to split the US population in 2 groups. It would be a good guess to do men, women, right? That's pretty much an even distribution. But if you apply this rule to this room, it would probably not work that well. So this is a kind of thing you have to take into account when you're choosing a load balancing mechanism. And overall, the more granular your mechanism is, the most likely from a statistical standpoint, it will work fine at producing an even distribution. Let me show you the example, you'll understand what I mean. So we have this explicit failover mechanism. This is something that has a granularity of a DV port group. We're talking pre-NSX, I forgot to mention. We have this little green tag on the top. So here I'm pinning a DV port group to a particular uplink. And if those DV port groups are generating the same amount of traffic, I'm good. But I can do more granular by now pinning VMs to a particular uplink. So now with a source port hash, I can have within the same DV port group, I can now be more selective and have VM1 that is going to the left uplink and VM2 that is going to the right uplink. the method is going to produce better results because you have more VMs and DB port groups. Again, the size matters in terms of statistics. And the last model is even more granular. It's the granularity at the level of a flow. So same DB port group, same VM. Now, within the traffic that this VM sends, I'm capable of differentiating between flows and pinning them to different uplinks. So just a high-level overview of the kind of mechanism that we're offering. And the first one, the explicit failover, applied to VXLAN. Our VXLAN network is a little bit particular. I told you you're going to pin a DB port group to an uplink, but now all your traffic is going to the same VTEP locally on a host, and it's backed by the same DB port group. So you don't have variety in DB port groups here. So basically you end up with an active standby mechanism because my DB port group, at this level of granularity, my DB port group can only be pinned to a single uplink. And by the way, again, we're talking about recommendations, stuff like that. This doesn't mean that it's a bad model. Well, it has some very clear advantages. It's very simple to configure. It requires absolutely nothing on your physical infrastructure. And one characteristic that some customers like is that it guarantees a certain amount of available bandwidth in case of a single physical failure. So for certain customers, it is critical that I'm sure that even if one link fails, I still can guarantee the same amount of bandwidth to my clients, my users. Well, with this, you're wasting, if you want, potentially half of your bandwidth, but when one link goes down, well, there is no change in terms of bandwidth available. I put in second spot the port channeling mechanism. So this is the one that is flow-based. Potentially the most efficient, right? The most granular. Port channeling technologies also have the benefit of converging fast because a failure is a local failure and dealt with locally. There is nothing beyond those few links and the few networking devices involved. There is nothing else to notify in case of failure. So convergence is fast and potentially the load balancing is very efficient. That's not the one we're going to recommend as a first choice, and let me tell you why. The reason is that in order to make this work, okay, so we have a single VTEP. My VMs are talking to this VTEP, and now the VTEP itself is doing a flow-based hash and is capable of selecting one of the uplinks. The problem is that for this to work, we need to have a port channel. And port channel itself, I mean, so link aggregation, also, I mean, terminology might depend on a per vendor basis, but the port channel technology itself is very standard. It's been codified at the IEEE, no problem with that, and pretty much every device supports port channeling today. However, what we need here is a distributed port channel because we want a port channel that ends on two devices, not just on one. And even if you will read in the network manufacturer that it's using the industry standard, well, the IEEE standard of 802.1 something, the implementation of a distributed port channel really varies from one vendor to the other. It is not a standard. It is a relatively complex technology, even if it's simple to explain at a high level. And it is implemented inconsistently between vendors. The capabilities are different. So if you want to use what Cisco calls a VPC, some other vendor call NMLAG, that's probably very efficient, but we're recommending that you decouple again from the capability of your hardware and you just require the minimum feature set possible. And the way you would do that is by using the source-based hashing. The way it's going to work is that you have now two VTEPs. They're still backed by the same DB port group, but two VTEPs. And now your VMs are going to be pinned to either VTEP and use either uplink. Just a last mention before I switch over to Rajiv. I kind of lied earlier on when I told you that you could terminate L3 to the top of rack. Those two VTEPs have to be in the same subnet. And if you want redundancy, it means that this layer 2 domain has to extend between the two top of rack switches. This is something that will change in the future. It's not the highest priority, but we still require a little bit of L2 between the two top-of-rack switches. Again, local failure, global impact. Well, the global impact is still local to your two top-of-rack switches, so it's not that bad. It's a very good compromise. So still a good spread of traffic on a per VM basis. Configuration is still simple, doesn't require anything on your physical infrastructure, and no advanced feature required in the network. Well, you still need to be able to do bridging, but again, most switches are capable of doing so. So I will hand over to Rajiv, who will carry on with the monitoring and troubleshooting section.
Thanks, Francois. Good morning, everyone. I hope everyone's doing fine. So this section, we're going to focus on monitoring and troubleshooting, and that's everyone's favorite topic. So we spent a lot of time thinking about how we can make our users' life easy, and obviously we want to leverage the benefits of being in the VMware vSphere stack. And some of the benefits that we can bring to the table are the fact that we are closer to the VM. So we have visibility into the VM. Most other networking solutions will not be able to give you that. The second benefit that we thought we could bring to bear here is the fact that this is software. So once this is software, it means all the benefits of software are at your disposal. You can basically take snapshots of the entire network, and we can actually ship that back to our labs if there is a problem, and we can recreate your environment and try to see what is going on in the network. Another thing is centralized control management, which Francois touched very briefly in his introduction slides. So we have a global view of the entire network, and we can leverage that to actually give you one centralized entry point into the network to debug problems. But anyway, that is the NSX philosophy of debugging, trying to make it easier for you guys. Since this is a VDS-specific session, we wanted to focus on the VDS tools. Now, VDS itself has a bunch of features that are available in general in networking. So I wanted to focus on two tools. One is VXLAN ping, and the other one is Traceflow. So before we start on that, who in this audience has not used ping? So as expected, great. So we don't have to explain ping. VXLAN ping is very similar to your regular ping. What does it do? It basically allows you to test connectivity between two endpoints. The way the workflow would go is, suppose you have two VMs and they are not able to talk to each other. Then you could go to the guest OS, issue a regular ping, and probably it fails. If it succeeds, then things are fine. If it fails, the next thing we want you to do is to check the VXLAN infrastructure connectivity. So we talked about VTEPs. So the VXLAN ping will make sure that your VTEPs are actually able to talk to each other. So if that succeeds, but your VM ping is failing, then you know that the problem lies between your guest OS and the VTEP. And that isolates the problem. It's good data to have. So again, in summary, the VXLAN ping is testing connectivity between your VTEPs. The way it works is we encapsulate a control frame inside the VXLAN header and send it from one VTEP to the other. So let's take this example. In this example, we have a logical switch, the blue logical switch, that has its physical representation across 6 hosts. So you have host A through host F. These hosts are actually on 3 different subnets shown by the different colors. Let's assume that you want to debug some problem between VM1 and VM2. So there are 2 kinds of traffic in general, right? There's unicast traffic and there's BUM traffic, broadcast, unknown unicast, and multicast. So these 2 kinds of traffic take 2 different paths. So the unicast traffic is pretty straightforward. So the unicast traffic, the way it works is, in the workflow, you can choose whether you want unicast or broadcast traffic. If you choose unicast traffic, then the ping essentially would go from host A directly to host D, because in our software, we know that VM2 is sitting on host D, and we know the IP address for host D. So that is straightforward. It is very analogous to what happens in your regular ping, the ICMP echo request and reply. The next one is the broadcast traffic. Now, the way broadcast traffic is handled in a logical switch, or in a regular switch, I should say, is that every endpoint, it basically floods. Every endpoint needs to receive the traffic. So how do we do that? We do it in 2 stages. So the first stage is our stage 1 replication. So the host essentially sends 1 copy to every single subnet. So that's basically what's shown in the first step. After that, each host, for example, host C, which received that copy, would respond back to the source, which was host A, saying that I got it. And it in turn would forward that to all the local elements of that logical switch that exist on its subnet. So that would be the second stage. And then each of the second hosts would respond back to host A. So that's pretty much how the 2 different kinds of traffic are handled. Your regular data traffic goes the same way. Our ping also, VXLAN ping also follows the same path. So there's a ping demo, and by the demo, I want you to get an idea of the workflow. The technology behind it is exactly what I explained in the slides before. So this is again using the same example that Francois had of the data center, and we're going to go and double click on the logical switch, and you'll get to the monitoring troubleshooting pane. On that, you can basically choose ping. I'm just going the example of the logical of the unicast ping. The first time I'm going to choose 2 hosts which are not on the same logical switch. So when you issue the ping, it's going to fail. And we'll start the test. And there you see that it fails. And you can go and select 2 hosts that are part of the same logical switch. And that will succeed. And that tells you that things are fine. So that's, there it succeeded. So that's pretty straightforward, easy to understand. It's a very useful tool. And the reason I wanted to highlight that is it will give you a quick way to isolate the problem, whether it is in your network or whether it is at the host. So this tool will be able to tell you that. If your VM ping from the guest OS is failing, but the VXLAN ping is succeeding, then the problem is not in your network. It's probably somewhere in the host. So that was one good tool that you can use. The next one is Traceflow. Now, before we get to Traceflow, I want to talk about packet capture. So packet capture is this amazing utility that we developed, again, because our solution is completely in software. There are things that we can do that is difficult to recreate in the physical world. Packet capture at a high level allows you to insert capture points into our stack. These capture points in our stack, places where you can insert the capture points are basically you could do it at the VM NIC level, the VNIC level, the VMK NIC level, the uplink level, and there are a bunch of other points, but these are of interest over here. And once you have gotten these capture points, you can actually specify rules and filters about the kind of traffic that you want to capture. And once you have captured the traffic, you get the output in a PCAP format. You can connect it to a Wireshark, and this shows you the pipeline. So as the packet is traversing our stack, you will actually see the output of how the packet is getting edited. So if there's some bug somewhere in our code, you'll be actually able to see, hey, I expect it to get encapsulated with this IP address. You would then probably see that it's not getting encapsulated that way. So that is host level packet capture. So Traceflow, which is the second tool that I wanted to talk about. Traceflow uses VXLAN ping and host packet capture. So how does Traceflow work? It is very similar to Traceroute, or I should say it is Traceroute on steroids. So how many folks have used Traceroute? Okay, pretty much the whole audience. So that's great. So you will get this. What it does is Traceflow essentially allows you to trace the path of the packet is taking. And in case of the broadcast traffic, it will show that the host A, the first replication point, as well as the destination. It will show you all these 3 points. The second thing it does is it incorporates packet capture into the tool. So what you can do is you could look at the output, and as the packet is traversing, not only do you get things like the IP addresses, the hops, you can actually see different stages of the pipeline, and you can see how the packet is getting edited. So this gives you like a representation of our entire pipeline. It's pretty amazing a tool. And again, the output is in PCAP format. You can connect it to Wireshark, and you can take a look at it. So how does it actually work? There's a few steps involved, and we have simplified all of this so that it's just one command for you. But just to give you an idea of what's happening in the background. So again, you go to the controller. So you don't have to go to individual hosts. So once you go to the controller, you pick the logical switch that you want to debug the problem on. You pick the source host and the destination host, whose path you want to make sure that things are working fine. Once you issue the command, what happens is the controller, the logic works this way. It sends the command to the source host, enables it, preps it for packet capture, sends another command to the destination host, preps that for packet capture. It configures the rules, sets the points. You don't have to do anything. It takes care of it for you. It sends the message to both the hosts to initiate ping. This is a bidirectional ping. Again, traffic from host A to host B may use one path in your network, and host B to host A may use a completely different path. So we want to make sure that bidirectionally you're able to actually debug the problems and get the packet trace. So we initiate a bidirectional ping. Then it sends a stop command to stop the packet capture. It sends it to both the hosts. The results are collected and they are sent back to the controller, and you would basically be able to see the output. So this entire state machine, again, has been abstracted out. You guys don't need to worry about it. It's just a simple command that you would run from the controller. So the next demo gives you a workflow, it walks through the workflow of how this thing works. So the demo is in 2 steps. In the first demonstration, what we are doing is we're not giving you the packet capture output. It's just the simple output which says the ping succeeded. And the second demo will actually give you the output of the packet capture. So let's start again. Here again, we are looking at, it's the same example. This is our ABC Medical Data Center. You can go to our hands-on lab and look at the same setup. Again, we are trying to debug or trying to show an example between those 2 hosts that had web switch 1 here. So this is our NSX controller. You go to the console of the controller, and I think the first command will basically show you the logical switch. In this case, it shows the logical switch and the connections of the VMs on that logical switch. The next command is to basically start the ping. I don't know if it's very clear. I hope it's, apologize for the fidelity of the video. But essentially what that is doing, that is initiating the ping. It has the results of the ping. The state machine ran in the background. As you can see, there are 4 outputs because it's a bidirectional ping and you're doing capture from both the destinations. The second output essentially, and these are the PCAP files. So you could actually connect these files to Wireshark and you would be able to see the packets that is being captured at the destination. So this is the first one. It's pretty straightforward. You just get the results. It's similar to the VXLAN ping, just shows that I received the packet. The second one is with the packet capture option. There's just a display option. If you just set that to 1, packet capture has been configured automatically for you. And the output is captured in that file that I've highlighted over there. So even the show command is given as part of the output, so you don't need to figure out where the files are stored. And once you issue the command, you can actually see the output. I'm doing a dump of just the sending host. You can see the function names. These are the function names which we highlighted of packet capture, which says that the packet went through the uplink, it went through the VMKNIC, it went through the VTEP. So that's the entire demo. So we haven't integrated this into the UI yet. It is only available as part of the CLI. So that is one thing that is on the works. It's on the roadmap. The other thing, limitation of this thing is right now it only works on a logical switch. So it doesn't work across a router. So that is something, again, that is on the roadmap. We're also planning to integrate it with the firewall and other modules. So that will give us an end-to-end visibility for the entire NSX suite. So this is available in 6.1, which will be coming out, I think we announced it in VMworld. So that's the next NSX release. So I think that's pretty much what we wanted to cover in terms of the deep dive and recommendations. There are a few other recommendations. In terms of security, we don't have time to go over a lot of the security. We actually have full sessions. And I'm sure you guys, if you have not attended it, which talks about the distributed firewall, deep dives, and microsegmentation use cases, we highly recommend that if you haven't already visited these, and if I'm not sure if they're playing today, you could go and check out the slides. That's an interesting, very interesting topic. Other one is on QoS. You can set the QoS through DB filters on the encapped packet. So we recommend that you do that if you want to basically distinguish between different kinds of traffic types. That is one feature that is available. MTU requirements. Now, again, as we mentioned, this is an encapsulation technology, so we are adding some overhead. So by default, when you create the logical switch, our MTU is set to 1600 on the host. So we recommend that you do the same on your physical infrastructure, if not already. So that would be one change. And finally, on the NICs, I think Francois already talked about it. We have some vendors that do offloads for VXLAN. So if you want better performance, then we would recommend that you install those NICs on your systems. We also have a session which goes into a deep dive of the performance and gives you more details. Welcome to attend that session. And again, if the session has already been done, then you can check out the slides. So in conclusion, the VDS is the key component in the NSX platform. It is the data plane. We have enhanced the VDS to work with NSX, and that we have added some few kernel components to that. And the key takeaway with the entire NSX story is that we have decoupled ourselves from the physical infrastructure, and I hope that based on these recommendations, we support all the different kinds of capabilities that your hardware may provide you, so that once you configure your hardware, you don't have to go back and touch it again. And again, the VDS is capable of scaling to large data centers and allows you to manage it centrally. So next, you can go and check on the hands-on labs. So the demos that we showed over here, I think you can actually go and try them out. So you can try out these things. In the lab, specifically, there is an NSX lab. You can try that out. And we also have a booth. And you can come down to that booth and check out all these demos that are running continuously in the background. So we can take questions. I think we have a few minutes left for Q&A. So any questions in the audience?